when we are calculating delta G at standard states, we have two options. If we are at 25 degrees Celsius, we can go to the chart and use the delta G's of our products and reactants, subtract them like always, and we'll get that value. So again, we would go to our table here, we would find the delta G's of interest, we would have those values, and we would go ahead and do the math associated with them. Just be aware delta G for standard states, for elements in their standard state, is 0. Alternatively, if we were so inclined, at any particular temperature, we could calculate the delta G using the following formula, the main equation that we looked at this chapter. Delta H is delta G, let me try again. Delta G is delta H minus T delta S. There we go, I can do it. So you can use that for any temperature. So, as always, let's go ahead and do this for our favorite reaction. Let's go ahead and evaluate our favorite reaction at, why don't we do it at 25 degrees Celsius. We'll do it both ways. So, N2 plus 3H2 turns into 2NH3. I think after writing this so many times I would have it down, but no. Delta G for this would be 2 times the delta G for ammonia. We don't need to include the others because they would be 0, because those are elements in their standard states. So let's go ahead and find ammonia on this big old table. Mercury here, here's nitrogen. Here is ammonia gas. Delta G is negative 16.4. I'm going to write that down. We'll go ahead and use that value in just a second. Negative 16.4. All right, so we've calculated delta G. I'm also going to write the values for delta H because we're going to need that as well. So delta H for ammonia is negative 45.9. I'm going to write that in the corner. We have nitrogen, its delta S is 191.6. And then the S for ammonia, I'm just gathering all the data here. The ammonia is going to be 192.8. We're going to get all of this data so we can put it all together, and I'll show you how to use both equations. And then for hydrogen, delta S is, I lost it, 130.7. Okay, cool. Back to the tablet. So that's how you look stuff up as well. You'll go, here's hydrogen gas. Let's go and find the S associated with it. It's always delta H, delta G, delta S. So here we go. I have the numbers written down. Delta G for this reaction, if we use the first way of just going ahead and solving this, we'll get negative 32.8. So this is kilojoules per mole. Great. So we've calculated delta G through that manner. We can also calculate it using delta H minus T delta S. And we can plug in all of these lovely things to figure it out. Delta G for this, delta H for this reaction would be, looks like negative 45.9 times 2. That's our delta H. Delta H for the other two reactants, again, does not matter because they are in their standard states, so we don't include those for delta H. We're going to multiply this by negative 298 multiplied by our delta S, which is going to be, remember we have to calculate that using the molar entropies, which actually we had calculated earlier. Why did I even bother? All right, let's go ahead and scroll up to where we calculated this delta S. We calculated it to be negative 198.3. Hooray. Problem solved. Negative 198.3. Note here we have joules per Kelvin, and we have kilojoules. There's also moles here per mole. So we're going to need to break these apart into their respective base units so we can work with them. So we have 91,800 joules per mole minus let's go ahead and do the calculation. Remember, we're going to add plus because we have two negatives. 298 times 198.3. We get 59093.4 joules per mole, because the Kelvin will cancel out. And adding that together, minus 91,800, we get negative 32.7 kilojoules per mole. Hooray! Notice these numbers are very similar to each other. There's probably just some rounding happening here. We calculated it both ways. They both work. However, the first way of just looking up the delta G in the table is only at 298. If you need it at a certain temperature, you're going to have to use the delta H minus T delta S. So both of them should give you the same answer at the same temperature. And indeed, just some errors here in my math. We have slightly different answers, but that's all right. So we can calculate delta G. But what do we do with it? What do we do with this delta G? It turns out that the delta G for a non-standard conditions will be equal to the delta G at standard conditions plus an adjustment for where our reaction happens to be. So we're going to see that if we are at somewhere else in our conditions that are not standard, standard means 1 atmosphere or 1 mole, a molar rather, of your reactants and products. If that were the case, Q would be 1, ln of 1 is 0, so that whole thing, delta G, would equal delta G standard if everything is standard. But if things are not standard, meaning we have not 1 atmosphere of everything, we can figure out what's going to happen. So let's say, so this, by the way, this value for delta G, the negative 32.7 or 32.8, that would be for nitrogen, hydrogen, and ammonia all at 1 atmosphere. And so this reaction tells us that delta G is negative, so it will be spontaneous in going forward to produce some ammonia. That's happening here. If we want to figure out what it's going to be at some other point in time, if we had different amounts, we could do that. Note that Q, by the way, must be QP for gases and QC for solution. Don't use, we're not going to use gases as concentrations this time. We're only going to use pressure for gases because we have that that R in there. So we're going to have to make sure that we have our units correct here. So just make sure that you use atmospheres for gases and molar for solution, and not the other way. So don't use gas concentrations as we have been able to in the past. So with this, let's say we have this is a very important equation, by the way. I would make sure you remember this one. Write it down, sticky note on your wall. All right, so let's say we have, let's see, atmospheres. 1 atmosphere of nitrogen, 3 atmospheres of hydrogen, and 0.5 atmospheres of ammonia. This is from our book. We can do this. And we're at 25 degrees Celsius. Let's calculate what delta G will be at this point in the reaction. So this is not necessarily equilibrium. We don't know that, right? Equilibrium, I'm going to just say we're not at equilibrium. Okay, we're going to just use Q. So with this in mind, delta G would be equal to delta G at standard conditions plus our RT. Notice for R, we're using the 8.314 version because we want joules out of this. We want energy, not liters and atmospheres. And then the temperature is 298 Kelvin. And then we have the ln of Q. The Q we're going to have to solve for. Remember that Q is going to be our reaction quotient, products over reactants. So we have our ammonia squared over our hydrogen cubed and our nitrogen, which will be 0.5 squared over 1 times 3 cubed. I'm going to use the calculator. 0.5 squared divided by 3 cubed. All right, Q in this case is 0.00926, we'll say. Let's plug that into the formula and see what happens. See, we don't even need K here. We don't need to say, Q is less than K, Q is greater than K. We can use delta G directly. We don't even need to bring K into this. So, delta G. Our delta G naught, the one that we found earlier, let's use our negative 32.7, and let's bring that into our regular joules again. That's the value we calculated before. We either used delta H minus T delta S, or we used the regular delta G's from the back of the book. All right, so we have that value plus the 8.314. I'm going to just omit the units because we've got them up here just so I can have the space. And then we have the natural log of 0.00926. All right, plug it all in. Let's see what we get. So, natural log of my answer, I'll do that first because I have it already in the calculator, times 298 times 8.314. Add that to our negative 32,700. We get, in fact, negative 44.3 kilojoules per mole. So, this is in fact definitely more spontaneous towards our equilibrium. It's going to go further forward in producing those products. So we can use this to calculate the Gibbs free energy and what's going to be spontaneous or not at any conditions given for whatever reaction we have. So very useful. We can calculate delta G naught, the standard delta G, by using one of two methods. Either look in the back of the book for 25 degrees Celsius, or we need to calculate it using delta H minus T delta S for any temperature. Once we have that, we're going to use this relationship here to evaluate non-standard conditions. At standard conditions, delta G is equal to delta G naught because Q will be 1. Everything will be 1 atmosphere. So it doesn't matter what our exponents are, everything will cancel out. We'll have 1 as our Q. Natural log of 1 is 0, meaning the RT, ln Q becomes 0. And so delta G is delta G naught at standard conditions. At non-standard conditions, when we have not 1 atmosphere of everything, or not 1 molar of everything, we need to use this equation to determine delta G. So at these pressures, the reaction is still spontaneous towards formation of ammonia. Ooh, what a fun thing. Definitely take a break before the next one, because we're going to bring in now K into this.